Interpretations of the rotation matrix. There are basically three different interpretations. The first one says that a rotation matrix is a representation of the orientation, and it is what we have been seeing before. So it represents the relative orientation between two reference frames, for example, between A and B. This is the matrix that we have seen before. The first interpretation of this matrix using this notation is the following, that it represents frame B in terms of frame A. The second interpretation needs to be considered very carefully, and it says that this matrix takes frame A to frame B. So it takes frame A to frame B. Why is this true? Because we are starting with the reference frame A, which is canonic in A. By canonic, I mean that it has as vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, and we end up in frame B, which is given by the coordinates of B in A. So this matrix gives the coordinates of B in terms of A, or equivalently, it takes A to B because it's representing B. So this is another interpretation that will be useful later. The second interpretation says that it maps points between frames. So it represents the same point in different frames. Here we have the same point in different frames. To begin with, let's consider this point in frame A. And we represent this P with the superindex A, meaning that it is in frame A. So this point in frame A will be XA, YA, ZA. We can represent this point as this one, which means that we are using this coordinate in the direction of XA, this in the direction of YA, and this in the direction of ZA. This is exactly the same. Both notations mean or represent exactly the same. We can have the same point now in frame B. In frame B, we have this point, and we have again coordinates, but these B's mean that this point is represented in this frame B. It can again be represented also in this way. Both ways are the same. Now what we want is we want to start with point B and represent this point in frame A. So we want to obtain the coordinates in A. This is the objective. How do we do this? Again, we have to project the point on every axis of A. So we project the point, we have point B, we are projecting this point B in A. If we project this point B in A, what we will obtain is the following. First, we should consider that this point P in B is given by this expression. So we want the dot product of this with XA. And the dot product will be this dot XA, this dot XA, and this dot XA. So we will get this expression. We do the same for all the coordinates of A. So for YA, we get this, and for ZA, and we get this. So in matrix form, we can rearrange this, and we can just obtain this expression. This is exactly the same. It's just a rearrangement of this. And now you can see that what this is a rotation matrix that we have seen before, and it is mapping the point between frames. We start with frame B, and we end up in frame A. So to conclude this part, this rotation matrix from B to A maps points from B to A. Similarly, we can do the opposite. We can say that this rotation A to B maps points from A to B. And recall that this holds true, that we have that the transpose of B in A is equal to A in B. As an example, let's take a look at this. Let's determine by inspection the coordinates of point P in frame B. In frame B is the red frame. So by inspection, the coordinates are D2 in XB and D1 in YB by inspection. Now we want to find the rotation matrix that relates both systems. So the rotation matrix will be given by this. Now why? Again, if you recall, we have B in A. So we want to represent the axis of B in terms of A. So X sub B is equal to Y sub A. So we have 0, 1, 0. Y sub B is equal to minus XA. So we have minus 1, 0, 0. And ZB is coincident with ZA. So we have 0, 0, 1. Now what we have to do is we have to multiply the point so that we transform it from B to A. So we have to do this. Now we can do this numerically. We just replace the numbers and we obtain this. And you can verify by inspection that this holds true, because in the frame A, which is the black one, you can see that in X there is minus D1, and in Y there is D2, which is what we obtained, minus D1 and D2. The third interpretation is as a rotation operator. This means that it rotates a vector within the same reference frame. In this case, we are not changing reference frames. We are keeping the same reference frame and we are rotating the vector. In general, it rotates vector p1 and angle theta about axis k. This k is any vector. Usually it has to be a unit vector to obtain p2. In this case, the notation that we use is this one, which makes it obvious that the rotation is theta degrees or radians about axis k. As an example, we want to find the resulting vector after rotating vector p1, which is 0, root square of 3, 1, and is this point that you see over here, and angle 30 about axis x. So we want to obtain this point p2. First, we will obtain the rotation matrix of 30 degrees about x. We just replace the numbers. This is the canonical rotation about x, and this gives this value. Then we can apply this expression, and we can rotate point using this expression. So we do this. We just replace the values, and we will obtain this element. You can verify this by inspection. So you can do some geometry here and verify that in fact this holds true.